I'm dividing 2.4 up into sections because I realize a lot of this is going to be review for certain students. So feel free to skip any video that you feel like you already know everything in that particular section for. I will not be checking notes for 2.4, only for the other, for like 2.5 will be where I start checking notes. So we start with measuring center. This tells us what the average, right, in quotation marks, the average person might spend on groceries, or what the most common amount that people spend on groceries is. That we unfortunately can't use those words anymore because average means mean and most common means mode, but you kind of get the idea, right? We're looking for what describes the sort of most common or most natural or most normal outcome for our data set. We have 3 different ways to measure this. One is the mode. This is the most common thing, the thing that appears most often in the data set. Makes sense in histograms, right? When we have binned data. Also makes sense if we have a data set without a huge number of unique values. So those students working with number of siblings on Tuesday's activity, this was something that would have made sense to use. Like, what was the most common thing? What's our mode? But most of the time, we're dealing with data that is a little bigger, has a lot of unique values, and the mode is not very meaningful. So we will still talk about the mode in histograms and in that setting, but in the setting of working with a data set and trying to summarize it, usually the mode is meaningless. So we move on to the mean, our average. I know all of us know how to take an average. 2 things I want to be able to do in this particular section. The first is to get us comfortable with summation notation. So if you've taken higher math, you already know what all this means. If you haven't, this might be a review or it might be completely new to you. So down here, we have 2 formulas, sample mean and population mean. First thing, since we do have this distinction between a statistic and a parameter, right? We have different names for them or different ways to denote them. Our sample mean we denote as X bar, where we put a bar over the X. That tells us it's an average. This is very useful. It's used a lot. And then when we're talking about our population mean, we use this Greek letter, which is called a mu, to talk about our population mean, our parameter. Both of these formulas are pretty much identical, right? On the right-hand side, you can see the formula looks just like you would expect. Add up all the values, divide by the total number. Add up all the values, divide by the total number. We do have some other notation issues. Our n is a sample size when it's lowercase, and it's a population size when it's uppercase. But I don't care about this side. This is how we all think of usually our mean. That's great. I want us to start getting comfortable with this summation notation. So first piece that we need to know about this, we obviously are taking 1 over n and multiplying it, which is the same thing as dividing by our n that we see over here. But the next thing we come to is this giant, what we call an uppercase sigma. And this is our summation notation. In fact, I will try not to call this sigma anymore because we're going to have a sigma later. So this tells us that we're doing a summation. So whatever comes behind that, that's what we're summing. So in this case, we are going to be summing up these little xi's. And these xi's, well, that subscript is just telling us grab the ith, and they are the observations from our data set. So to give us an example of what the heck that xi means, in this little data set below, x sub 2, right? So you're at the 2 little tiny below. X sub 2 would just be the second piece. So 1, 2, it would be 11. And x sub 5 would be 80, right? So ith just means second, fifth, whatever it might be. Our i's, well, this is what we have in terms of our indexes on our summation. We are going to start with 1, and we're going to add up until we get to n, until we get all of them, right? So I is going to go from 1 up to 2, 3, all the way until you get to lowercase n, our sample size and our sample, or uppercase n, our population size and our population. So the idea, again, if we can understand the summation notation for something we already know how to do, it's going to make it that much easier when we go to the standard deviation formulas in a couple pages. Second thing I want us to do is to understand what an outlier does to our mean. And we should have gotten that out of the JITT before Thursday's class. But I've given us a small sample here just to try this out. So we're going to go ahead, find our average. So we'll do our summation, add all these things up. First up to the, oh, I'm sorry, I said 5th. This was 6th. Woo! I did not actually count how many things I had. And then divide by my total number. This will allow me to find my sample mean. If I do all of this math, I get 25.83, I think. I double checked. It's right, 25.83 with a 3 repeating, but we'll just leave it at 25.83. Now, this is the same question I asked in the JITT. Is this a good measure of the center of this particular set? And see, again, center is a hard word to use because when we hear center, we think middle, we think median. So this center, average, common, like it's hard to define what that means. But I think all of us could agree that 25.83 is above the majority of our data. It is not representative of these 5 points, right? If this was the amount of money people had in their wallet and we said everybody had $25, so it'd be great if we did a football pool for $20, well, we're going to not have everyone be able to put enough money. This happened to me in the Super Bowl. They were like, oh yeah, let's pick squares. Everyone give $10, and no one had cash on them. So this would be a problem, right? You say, okay, $20 for all the squares. 4 of your 6 people wouldn't be able to afford your little football pool. So this is not the greatest measure of center. And this is exactly what we saw in that JITT. Everything has examples of this. One of the most important examples of this is income. If you're given a measurement of average income, that is going to be skewed. It's going to be pulled to the right usually because there's always a couple of high outliers in terms of income. So the median is a better measure, especially when we aren't sure what's going on or we know that there's going to be a skew or some outliers. You can imagine here if our value, if we had this as an 800 and then did our average, then all of a sudden our value is going to be in the hundreds. And that's really far off from what the rest of the data is telling us. So this is the thing that you need to know for a test. What I like to test on are these 2 bullet points. This idea that our sample mean is influenced by a skew, that it is sensitive to outliers, and we should only be using it when we have nice, pretty data, and that is a symmetric distribution without outliers. All right, so that's our mean. The other measure of center, the actual center, the median, is the middle, right? The halfway point where half of the values are above and half are below. So I have this little spiel here on how to use this little position formula so that you don't have to look like a nerd and sort of like count in with your fingers until you find the middle. Obviously, with the small data sets that are given as examples here, this is silly, but I just wanted to show it working really easily and quickly. So that's what we have. So we're just going to practice this position formula really quick. Here you can see we have 5 observations. So if we were to use our position formula, 5 plus 1 over 2, this is the position of the median. 6 over 2, or 3. The third thing, that's our median. Obviously, we could see that, but this is just a kind of way to do this by hand. If we have an even number, what happens with the position formula? In this case, we have an n of 6. You get 7 over 2, or 3.5. When you count over, you go 1, 2, 3, and your median is directly between 15 and 19. And I'm sure a lot of you remember from like whenever the heck we learn about medians that we then take the 2 to either side and average them to find that our median is 17. And you'll note here that this was no mistake. I used the exact same data set from the previous page to show us, oh, 17, that's a much more reasonable measure of center than $80, right? Or 80, I'm sorry, I'm still thinking of my Super Bowl example, than the 25 was, because it's not being affected by this 80. And even if I were to go ahead and add an extra 0 and make that 800, my median is still going to be 17. So our median is resistant to outliers. It is going to be our best measure whenever we're dealing with skewed distributions or distributions with outliers. So again, this is the thing I like to test on. What should we be using for this data set? Should we use the mean or the median to talk about the center of it? And it's all about whether we have pretty data or ugly data. The other thing I love, ooh, no, I did that thing again. The other thing I love to test on is the difference between these and what the effect of an outlier or a skew might have. So generally speaking, the mean is going to get pulled towards the tail of the distribution. Those couple of outliers, those high values or low values are going to pull the mean in that direction. So this I always then just make into a whale because I get bored and I turn lots of things into animals, as you'll find throughout the semester. So this is the whale tail question. And this is all about our mean getting pulled towards that tail. So the mean is the one that's susceptible. It gets pulled towards those large values. The median stays fairly put, even though, you know, our mode truly is actually a little bit still left of that median. This is not like a guaranteed thing to happen. If you have a distribution that's skewed to the right, it is not completely and utterly guaranteed that the mean will be larger than the median, but it is the most likely thing or very common to happen. I just note that the first time I've been teaching this for so long is like, this is the rule. And then I was working in my job and had a distribution that was skewed to the right, and that wasn't true. And I was like, whoa, I've been lying all these years. So almost always, but it's not guaranteed. Your mean should be larger than your median in the case of something skewed to the right. And if we're skewed to the left, it'll be the opposite. So then you'll just have your whale facing the other direction, right? But your mean is the one that gets pulled. And I'm obviously making it much more exaggerated there, but that's just to make it obvious. All right, so this is another task question. So this and what to use when are the two pieces that you really need to take away from mean and median.